Welcome to today's Micro-credential Topical Course. This course is funded by the Environment and Conservation Fund and organized by the Hong Kong Green Building Council. We would like to express our sincere gratitude to the Environment and Conservation Fund for their generous support. Today's topic is Beyond Aesthetic, Quantifying the Environmental Performance of Green Roof and Wall for Hong Kong Green Building Assessment. We are honored to have Dr. Yao from the School of Architecture at the Chinese University of Hong Kong as our speaker today. Now, let us welcome Dr. Yao to begin her presentation.
Thanks for the intro and the warm welcome of Hong Kong GBC. I'm honored to be here to share this micro-credential topic course with you guys here and the audience online. So before our lecture, I would like to give you a brief introduction of myself. I'm Lin Ye. I'm a postdoc research fellow from School of Architecture, the Chinese University of Hong Kong. I got my PhD in landscape architecture, and my research focuses on urban green and blue infrastructures, investigating how to use these infrastructures to improve outdoor SIAM environment, human SIAM comfort, health and well-being, as well as the energy performance. I have been working on the green roof and the green wall since my master's degree, and for now, I'm working on the IF project to investigate the climate change impacts on the older populations, and the green roof and the green walls are one of the adaptation and the mitigation structures. So now back to our lecture. Today we are going to explore how to quantify the environmental performance of green roof and the green wall, moving from seeing them as decoration features to understand them as engineered nature-based solutions. Here is the course outline. Our course will cover 4 main parts. We will start with an overview of green roof and green walls in Hong Kong, including the overall situation, the public acceptance, their typologies, and the detailed biophysical processes, and some key design considerations and the relevant guidelines and some reports. Then we will dive into the metrics we use to measure the performance. After that, we will introduce the commonly used assessment method, including field monitoring, laboratory experiments, and of course, numerical modeling. Finally, we will look at how this quantified performance translates into credits on the BAM plus Green Building Assessment Framework. And for your notes, we will have 20 minutes for questionnaire and lastly have the Q&A session. So let's get started with the first part, the overview of the green roof and the green wall in Hong Kong. As we all know, Hong Kong is one of the most compact, high-density cities. At the same time, it has a hot and humid subtropical climate, which means it experiences stronger solar exposure, and therefore it has serious urban heat challenges. As a result, green roofs and green walls can work as strong mitigation structures for heat mitigation. Green envelopes such as green roofs and walls have become important tools for green roof design and for heat stress mitigation in Hong Kong. Researchers and professionals in the academic and industry have done a lot of work in green roof and walls. And here is the literature for the overall situation of green roof and green walls in Hong Kong. According to the literature, for green roof, more than 300,000 rooftops in Hong Kong have been identified as candidates for green roofs. And around 90% of total roof area could be potentially retrofitted for greening if we consider the following factors such as building age, roof slope, planarity, and size. And among these, nearly 70% of roof area show urgency for greening. For green walls, also named green facade or vertical greening, it is primarily applied in high-rise facade, podiums, and noise barriers. However, the current implementation is still limited and project-specific. We can only see these green walls on the private projects and public developments. Here are some examples for green roofs in Hong Kong. The first is the Kai Kris Terminal Park building. It is a well-known excellent renovation examples. And of course, there are some other commercial examples like Ocean Park. The third photo is taken on the rooftop of our school building in HK campus last summer. We have developed the green roofs and the walls on the rooftop. And as you can see, we have harvested some small potatoes. Unfortunately, it is not under reconstruction. And here are some examples for green walls in Hong Kong. We can also see green wall examples at the City Walk into One and the Hotel Icon near Honolulu and the K11 Museum. These examples are designed at different scales and building types in practice. However, public acceptance is also very important. Here is a survey study that compares the public acceptance and the preference towards green roof and the green walls among the between Hong Kong and Beijing, led by Professor Jim. This survey conducted from the four aspects, including the greening attitude, current concern about negative impacts, policy preference, and the role of government. The results show that Hong Kong residents show stronger recognition of green roof and green wall benefits, but they have lower enthusiasm than other cities. Second, young and well-educated Hong Kong residents are the stronger supporter for high-quality green roof and green walls, and are key to build market demand and policy motion. This is a very practical and important message for us. A strong preference for policies that emphasize qualities. People prefer to have high-quality green wall and green roofs in terms of design, maintenance, and safety over the quantity. In a word, quality matters much than quantity. So before designing these high-quality systems, let's get some basic knowledge first. Here is the typologies for green roof and green wall. First, we can see the green wall typologies. We divide it into three main typologies. The first is the extensive green roof. This is an example from the Taipei railway station rooftop. It's a typical extensive roofs with lower substrate depths and with demand-low maintenance, and the less tree species with limited irrigation. And the second is semi-extensive. This is the second picture I taken in the 9 years ago during my master's program. It is with the substrate depth with 150 and 200 meters with moderate maintenance, and the stronger species choices such as shrubs and grasses, and it should be provided with seasonal irrigation. For the intensive green roofs, we have the highest substrate depth, higher maintenance, and the tree plant and the species are more options, but we need to regulate it, regular irrigation for it. Next is the green wall systems. We simply divided them into two systems. The first is the green facades, which is the climbing plants on building surfaces. It is often self-supporting or cable systems with lower cost, slow established, and it takes some time to grow and establish. The typical examples are as seen here, the electricity substations and the K11 Museum. And the second is the living wall. living world usually use modern systems with substrate active irrigation, and they have the immediate coverage, high maintenance, but it will always cost high. So next, we are moving to the biophysical processes to look at how these systems actually work, including the heat transfer, hydrological process, and the air quality aspect. As we can see from the picture, for the green roof, the heat transfer of roof can be divided into two parts. The first part is the heat transfer from the roof to the surrounding environment, which is currently for the concern of urban heat. And the second is the heat transfer through the roof to the building interior. It is always the concern for building energy use and the indoor environment. And the key heat transfer include the three processes. The first is the shading and the radiation interceptions. As we can see, the plants block the solar radiation. About 27 heat is reflected by the vegetation. And next process is the evapotranspiration. This is a combination of evaporation and transpiration from the plants and the soil. It will cool the air around the roof by covering about 60% energy into land heat flux into the outdoor environment. And then is the isolation and the reduced processes. The substrate and vegetation act as the insulating layer, reducing the heat conducted into the building, allowing only certain heat transmitted into the buildings. In summary, for the CM processes, vegetation and the substrate of green roofs often change the surface energy balance. They interpret solar radiation, convert some energy into land heat through evapotranspiration, and reduce the heat entering the building. Other processes such as the stormwater interruption and retention and carbon sequestrations. As a result, green roofs can improve outdoor CM environment, decrease indoor cooling load, increase hydrological resilience, and of course, improve the air quality by reduce the carbon emissions. And next is the biophysical processes of green walls. For green walls, they work through the similar processes as green roofs, but the special effects and the contribution of each component are different. The vegetation layer provides shading, interrupting radiations by about 5 to 30% reflected. It also cools air through the evapotranspiration by about 20 to 50%. The combination of plants, substrate, and air gap can provide isolation, reduce heat conduction into the buildings by about 5 to 30 transmitted into the building interior. So as a result, these processes above will reduce the wall surface temperature, decrease indoor cooling load, and improve outdoor CM at a pedestrian level. Other processes benefits such as stormwater interruption, reduce carbon emissions, and are similar as green roofs. So drawn from the biophysical processes, green roof and green wall have many potential benefits. These may be fall into three categories, including the aesthetics, environmental, and economical benefits. Although there are a great deal of cross-cover between these categories, for our course today, we are focusing on the environmental performance first. So the broader environmental benefits are significant. Recent studies show that the green roofs and the green walls can raise neighborhood green coverage, increase human exposure to green space indexes, ranging from 35 to nearly 50%, And it can also contribute to stormwater retention ranging from 23 to 78 due to the climate and the roof configuration differences. And the green roof can also help to reduce air temperature and therefore save electricity energies. The performance of green roof is valuable and can contribute to multiple scales, from the single building to the city scales. So next, in order to design high-quality green roof and the green wall, we need to look at some following critical design considerations. The first is the substrate depth. Minimum 100 millimeter is recommended to avoid the inversion phenomenon. The inversion phenomenon is where the dry and thin soil conducted more heat than exposed concrete. Here is the picture shows what is the inversion phenomenon, and we have 4 lines. The first, the light green is the 25 millimeter soil base, and the dark green is the 100 soil base, and the green line is the exposed membrane, and the orange line is the ambient air temperature. As we can see, if the soil is extremely thin and dry without irrigation, it will be largely higher than the total soil and the other exposed membranes and even the air temperatures. However, if it is irrigated heavily, we can see that the air temperature of the thin soil can be much lower than the exposed membranes. So the effectiveness of moisture cooling can gradually increase as soil depth increase from 12 millimeter to 200 millimeter, and the depth above 200 millimeter will provide no further significance in the ambient effect. Also, next is the irrigation structure. As we can see, as we mentioned in the last slide, this is critical for maintaining CM performance. A dry soil has about 1/3 of the eluting efficiency of moisture soil. As we can see in the left picture, the picture above shows the different energy balance between the 100 meter moist soil and the 100 dry soil. The heat conducted to the building through the dry soil is relatively higher compared to the moist soil. And in contrast, the moist soil is well covered with vegetation and well irrigated. As a result, a great deal of latent heat is reflected off, and it will provide good CM resistance. Therefore, irrigation is very important to maintain the positive CM performance. For the better irrigation structure, we suggested to use the automatic drop irrigation with moisture sensors for the extensive systems to achieve the better optimal performance. And next is the species selections. This is especially critical in Hong Kong's climate. The plants should match exposure conditions, shading conditions, and maintenance capacities. Here are some southern examples used in the extensive roofs in Hong Kong. Practically, we can refer to the practical guide to plant resources for high-rise greenery in Hong Kong. It has provided over 100 tested species. And here is the explanatory notes for these guidelines. In addition, a technical report called The Study on Green Roof Applications in Hong Kong by Arabs Limited also provides detailed plant selection metrics for intensive and extensive green roofs. And finally, we must consider greening systems with building integrations, including the structural loading assessment and the waterproofing integrity, drainage systems, and the maintenance assessment at the very early design stage. In addition, Hong Kong often faces typhoon during the raining season. The strong wind might blow away the vegetation and soil. Therefore, wind design is important to ensure wind uplift resistance for green roofs, and wind and light exposure is also should be considered for green wall. And for more detailed technical information, here we suggested referring the following technical guidelines for reports, including the technical guidelines for green roof systems in Hong Kong, and the benefits and the potential of vertical greening systems. This works all conducted by Dr. Hui from the Hong Kong U. For the hydrological performance, the extensive green roof first step towards sustainable urban drain system design in Hong Kong is suggested. It is conducted by the research team from PolyU. And here are also some guidebooks that showcase or recommended good examples of green roof and the green wall in Hong Kong. After learning some basic knowledges of green roof and green wall, this section is where we move from general environmental benefits to quantitative evidence. Here we will summarize some indicators for outdoor and indoor SIAM energy hydrological performance assessment. Based on the environmental benefits from the literature, here we summarize the 4 key dimensions, including the SIAM effect, the energy performance, and the water management, as well as the human well-being and the indoor environmental quality. For example, when we are assessing the SIAM effect of green roof and the green wall, we can see that they have cooled down the ambient air temperatures by about 0.5 to 2.5 Celsius degree. And we can also see they reduce surface temperature by nearly 70, improving the surface albedo. Therefore, improving the surface albedo. And for the energy use performance, we will use the building energy saving percentage to quantify their energy benefits. For the water management, the retention capacity and the peak runoff reduction are usually considered. And for the well-being and the indoor quality, we will look into the well-being improvement and the productivity gain percentage. And here is a brief introduction of performance metrics for each dimension one by one. Let's get first is the SIAM performance. SIAM performance can be described using several indicators. One is the ambient air temperature. For green roofs, we may examine the rooftop or canopy layer air temperature. For green roofs, we may examine the air temperature close to the wall surfaces. Another is usually commonly used is the surface temperature. This is one of the most instituted indicator. We often compare the surface temperature of a green roof or a wall without that for a reference base. And the third is the mean radiant temperature. It is frequently used for evaluating the outdoor SIAM comfort. We may also use the PET or UTCI, which combines several SIAM variables into a human-centered assessment of outdoor comfort. Then we have the heat flux, which tells us how much heat is moving through the rooftop to the indoor interiors, and it also tells us that the heat is moving inward or outward. Then we can also look at the CM resistance or the U value. They are all very useful information for the building series. And here is the table for the calculation for the U values with different building configurations. U value is the overall of CM transmittance. It represents how well an element conducts heat from one side to the other. As we can see, as the soil depth and the plants increases, the U value decreases. So it will sufficiently reduce heat transfer into the building. Next is the energy performance. Here, the main indicators, including the cooling load reduction, heating load change, annual energy use for space conditioning, consider the total HVAC energy use for cooling and heating, and the energy use intensities per floor area, and also the CO2 emissions reductions as the indirect indicators for reduced electricity consumption for cooling. In Hong Kong, cooling is usually the dominant concern, so most studies focus on the reduction of cooling demand rather than the winter heating benefits. A very important professional point here is that the same benefits do not always translate directly into large whole building energy savings, because the final energy effects depends on the building type, floor area, green envelope area, internal loads, HVAC systems, operation schedules, and the surrounding context. In other words, a large drop in surface temperature is meaningful, but it is not the same thing as a large drop in annual energy use. We need to keep those scales separately. Next is the hydrological performance. We will assessment this hydrological performance using the runoff volume, retention rate, substrate volume, water content, and the evapotranspiration rate. These indicators help us answer the questions such as how much rainfall is retained, how much runoff is delayed, how much water remains stored in the substrate, and how much water is returned to the atmosphere through evapotranspiration. This is very important in Hong Kong because rainfall events can be intense, and the green roof and green wall can contribute not only to the CM growth but also to stormwater management. At this point, we have a vocabulary of environmental performance. We know what to measure. The next section is about how to measure it. So let's move to the third part, assessment method, including the field monitoring, laboratory experiment, and the numerical modeling. Our focus will be put on the numerical modeling, as it is more useful for practical and fast assessment at the design stage. I will also introduce a brief model tutorial if time permits. So the first is the field monitoring. The field monitoring is the monitoring performance on actual building in actual weather over a real period of time. This may be long-term monitoring or short campaign-based observations. The strength of field monitoring is realism. We can see how the system behaves under real solar radiation, real wind speed and direction, real maintenance conditions, and the real building operations. And the data from the field monitoring can support model validation. So the first group of measurement is meteorological and microclimate measurements. The focus is usually the outdoor climate modification effects of green roof and green walls. This picture shows a standard meteorological weather stations on an extensive green roof to measure the commonly used meteorological data such as air temperature, relative humidity, wind speed and direction, solar radiation, and the rainfall above the roof or near the walls. And for the vertical greening or green walls, we may measure the air temperature and the humidity at different distance and heights above the roof or near the walls. And the third concern is the radiant environment. It can be captured using the global temperature and or more detailed 6-directional shortwave and long-wave radiation measurements. The second group focuses on the surface energy balance and the CM performance. Here we measure surface temperature using the infrared CM meter or CM cameras on the leaf and the substrate, and the radiation. We also measure the shortwave radiation and long-wave radiation to estimate surface albedo and the net radiation. On the building indoor side, we can monitor the surface temperature of ceiling or internal walls, the roof air temperature, heat flux from outdoor to indoors. So the field monitoring can link outdoor surface conditions to the indoor consequences. And here is the instrument for the detailed 6-directional short and long-wave radiations. And here is the picture for the irradiation CM meter cameras for the surface temperature compared between the bare wall and the living wall. So this slide shows the measurement results of temperature profile and the heat flux profiles between the reference roof and the green roof. For the upper picture is the air temperature roof. We have several lines for the different layers and the substrate, the members, and the ambient temperature and the indoor air temperature. As we can see, the green roofs the temperature lines of green roofs are much flatter than the reference roofs, suggesting that the green roofs can significantly moderate the daily temperature fluctuations. And the lower picture is the heat flux measurements show that the green roof can reduce the heat flow into the building. As we can see, green roof can promote the heat loss during the daytime and a little heat gain at night. And for the reference roof, it will gain a lot of heat during the day and loss at night. So the third group is the hydrological, focus on the hydrological and the water balance measurements. The focus will be the water, stormwater rotation, dentation, and evapotranspiration. We can measure the runoff by using the flow meters or tip bucket gauges. We can also measure the substrate moisture at different depths. Then, combining rainfall, runoff, and storage change, we can estimate evapotranspiration. This is very useful when the goal is to evaluate stormwater retention and peak runoff attenuation. And here is the detailed instrument and the site-specific configurations for the hydrological and water balance measurements. This is a research led by the research team from PolyU. So the fourth group looks at vegetation and the material properties. The focus will be the plant performance and the physical parameters needed for the models. This includes some vegetation structures, including leaf area index, leaf area density, and the canopy height and coverage. For the optimal properties, albedo and the emulsities are considered for the radiation method. And for the substrate physical properties, we usually measure the bulk density, porosity, and the CM conductivities. These measurements are essential parameters as meaningful numerical model inputs and model validation. And here is the detailed instrument for these measurements, including the professional instrument to measure the LAI and the LAD, and some traditional air temperature instruments and the 6-directional solar radiation measurements. And finally, field monitoring can also include the indoor environment and the comfort measurements, such as the room air temperature, relative humidity, global temperature, operative temperatures in the room on the green roofs or behind the green walls versus the controlled conditions. And for the radiation field, the surface temperature of walls and ceilings and the MRT using global CM meters are used. For the subjective surveys as the indirect indicators, the CM comfort questionnaire combined with physical measurement are often used to support the occupant surveys. And here is the indoor environment measurement, yes, covered with the green walls and the green roofs. And as we can see, we can employ different monitoring sensors in the door to illustrate the surface temperature and the air temperature distributions in the door. In summary, the field monitoring gives us a strong real-world evidence, but it also takes time, site assessment, and professional instrumentation, and need to carefully control their qualities. Alternatively, we can use laboratory experiment. So laboratory experiment allows us to isolate variables under controlled conditions. For example, we may compare different substrate depths, different irrigation conditions, or different green roof and green wall configurations using the text boxes. And the main advantages here is the control. In the field, many variables may change at once. So in the lab, we can vary one thing at one time and observe the response more clearly. Most importantly, it can support validating physical assumptions and generating data for modeling work. This makes laboratory testing especially useful for understanding the cause and effect relationship, and thus support the model validation. And here are some examples for the laboratory experiment. This study is the test box experiment of green roof to investigate the CM and the energy performance of a residential building. This is the text box. This team set up 2 text boxes to represent the scaled residential buildings, and the indoor conditions is controlled by the air conditioning, and one is vegetated with green, is planted with vegetations as the green roof cases, and the other is the controlled cases for without any vegetations. They are all put on the actual outdoor environment, and the only control is the indoor environment with HVAC. And here is the similar laboratory experiment with the vertical greening and the green walls to investigate the CM performance of green roofs and the green walls. And the scaled testing rooms are the similar as the previous one, and the controlled condition is the indoor environment for both boxes, and again they are all put on the outdoor environment. And here is the result for the experiment measurements. The orange lines represents the green cases, and the blue lines represent the controlled cases. And it is conducted on a typical summer day. As we can see, the green roofs and the green wall systems can significantly reduce the air temperature and help to improve the indoor CM comfort. Next is the laboratory examples for hydrological performance. Here is the experiment conducted by the research team from PolyU. The text boxes configured with different soil and plants combinations, and here is the example for the soil and the planted vegetations. And they are all put on the rooftop of the actual outdoor environment, and the only controlled condition is the rainfall rate with 10, 30, 15, 70, and 100 millimeter per hour to investigate the different rainfall events. And here is the professional instrument to calculate their retention rate after the rainfall event. And as we can see, with the rainfall rate increases, the improvement percentage decreases, but all the green roofs are behave better than the controlled ones. So in summary, the laboratory experiment can not fully reproduce the complex and the rare urban conditions. So although it is powerful, but it is not a complete substitute for field evidence. It will work better when combined with monitoring and simulation. So here comes the numerical modeling part. Why do we need to model? Because monitoring tells us what happened on one site and one set of conditions. Modeling allows us to test many what-if scenarios, such as the different urban densities and the forms, different urban green roof and facade ratios, and different substrate configurations, and different plant properties, all on the different weather conditions to test the typical or the extreme hot days. And for the commonly used models, we mainly have three categories. The first is the safety model. The open form, ANSYS, Phoenix, and MMAT are all the commonly used safety models for urban greenery. And for the finite element model, the Hydro 1D is a typical model for soil moisture transfer. And for the energy calculations, EnergyPlus is the main tool for building energy simulations. And here are some examples and good case studies for the numerical modeling. This study investigated aerodynamic loading of green roof systems on industry buildings using the open form. And here is the model geometry, and here is the result for the different aerodynamic loading on the different scenarios. As we can see, the authors use the three what-if scenarios, including the building and the parapet shapes and the wind, and it also changes the wind velocity and the wind directions. Next example is the CFD simulation case studies using ANSYS to investigate the cooling performance of vertical graining and natural shading devices. And this red plate is the vertical graining modeled in ANSYS. And here is with the different meshing schemes. So the what-if scenario in this study is the distance between the vertical graining and the wall. At the same time, the authors changed the weather conditions to investigate the different weather conditions impacts on the cooling performance of vertical graining. And again, this is also an ANSYS case study, but it investigates the influence of green roof and the green slabs CM conductivity on winter indoor warmings to investigate the indoor conditions. And here is the geometry model created in the ANSYS models. So the what-if scenario includes the green roof cases versus the base cases without green roof, and at the same time, the authors changed the winter weather conditions. And here is the results. The performance indicators including the CM conductivity and of course, the indoor air temperature distributions to see the CM impacts of green roofs on the indoor environment. And next is also the CFD case studies, and it uses the tool called Phoenix. It can simulate the pollution distribution indoor and outdoors. And this study investigated the PM10 pollution mitigation effects of green roofs and walls. And here is the geometry models in the domain. And the what-if scenarios. For the what-if scenarios, the authors considers the urban forms with different aspect ratio and the greenery coverage areas with different values and the vegetation LEDs. And here is the combination scenario tables. Based on the simulations, we can get that green roofs and walls can have the reduction ability to reduce the air pollution at the pedestrian level, and given the equal greenery coverage and the aspect ratio, green walls are more effective in reducing street level air pollution mitigation. And next is the numerical modeling. For the hydrological performance called Hydro 1D, it is a soil moisture transfer model, and it is different from the previous CFD model. It is a finite element model. So the what-if scenarios include the different runoff rates, including the following values. It is a reproduction model for the hydrological performance conducted by the Polio team. And here is the result for the simulation part, and this is the laboratory experiment part. After comparing these two results, we can conclude that the model tends to overestimate runoff retention or detention performance. However, when simulated for larger rainfall events, the model behaves better. Next, I would like to introduce you most widely used CFD model, EVMAT. As you can see on the right hand, a review study on urban greening related article shows that EVMAT is the most commonly used models among all the numerical models for urban greenery. And EVMAT is a high-resolution 3D model that simulates interactions among surface, vegetation, and atmosphere with the spatial resolution of up from 0.5 to 10 meters, and the temporal resolution of up to 10 seconds. For the latest version 5, AVMAT is equipped with improved modeling schemes for greenery. By using the mathematics to simulate the transfer and exchange of mass, energy, and moment, AVMAT can reflect the physical processes in the real world. So what can AVMAT do for us? As a user-defined tool, AVMAT can help with building, landscape, and urban design at different scales. For example, for the outdoor environment, it can calculate the air temperature, humidity, wind speed, solar radiation, and the surface temperatures. It can also support human CM comfort calculations such as PET, PMV, SET, and UTCI. In addition, it can simulate building physics to reproduce interactions between the outdoor microclimate and the indoor climate, and exchange process with vegetated walls and roofs. It can also be used to simulate the air pollution aspirations. So, as the most commonly used tool in urban greening study, AVMAT has strong implementations in vegetation modeling. This is the case studies for AVMAT to simulate the district scale, including the buildings and the vegetations at different scales. So for green roofs and walls, especially, AVMAT can have strong capacities for modeling. It can model evapotranspiration, CO2 intake, and leaf temperatures. And it can also, for the 3D plant model, the leaf area density distribution, vertical growth characteristics, and the canopy structures are also considered in its 3D plant models. Therefore, for green roofs, the model focus is heat and moisture transfer with building physical interactions, and for the green walls, radiation transfer through vegetation layers with substrate, and the wall substrate is the key capacities. And for the latest version, there have some enhancement for the greenery modeling. It is equipped with improved vertical greening simulation with actual plant growth patterns and the enhanced plant wall interactions modeling to support complex greening configurations for multiple species. And here is the illustrate to tell us what is the roof of solid greening in AVMAT configurations. It consists 3 parts. The first part is the substrate part. In the substrate part, AVMAT have the following parameters for user defined, such as the substrate thickness, emissivity substrate, and the albedo of substrate, and the water coefficient for plant, and the air gap between the substrate and the wall. And the second is the plant species using the simple plants. And the following parameters are considered, including the CO2 type, the leaf type, the albedo, transmission, and the plant height, root zone depth, RAD profiles. And also, you can use the seasonal profiles to set up deciduous or evergreen. The third part is the greening properties. It includes the plant thickness, RAI, and the leaf angle distributions. And here are some key important concepts in AVMAT. The first is the different possibilities to define model greening and the rooftop greening systems in AVMAT. This is a bare wall, and the first scenario is the wall with greening layers, the simple greening layers, without any substrate or air gap. And the second is the greening layer with substrate layers. And the third scenario is based on the scenario 2. We can also consider the air gap between the substrate and the wall. And figure 2 is the example for different approximated area indexes and the coverages for a green wall. For the relative thin vegetation layer, area can be understood as a coverage coefficient. As we can see, as the value of RAI increases, the tree coverage is increasing. And the third part is the water management of green roof and the green wall. In AVMAT, for green wall and roofs, it is assumed that a managed irrigation system is available to regulate and provide water to the plants, either on the roof or at the facade. As such, adjustable watering coefficient is defined. Here we have 2 scenarios available. Without a substrate layer, such as the greening wall in scenario 1. The examples are climbing plants. A consistent and sufficient water supply is assumed as 1. And the scenario 2 is with a substrate layer. In the case of 2 and 3, the watering coefficient can be defined for each greening system as constant factors that define both water content of the substrate and the water supply of the connected plants. So the value can range from 0 to 1. Furthermore, depending on the design of the greening system, a distinction is made between the 2 types. And next is the detailed biophysical processes of green wall systems in AVMAT. Here we illustrate 2 scenarios. The first is the simple greening without any substrate. And the second is the greening with substrate layer and the air gap. So as we can see, the relevant performance metrics, including the direct and diffuse short-wave radiation, long-wave radiation, sensible and latent heat flux, wind speed and air temperature, and of course the specific humidity. As we can see, comparing to the simple greening, the greening with substrate include more processes, which means substrate play a very important role in energy balance and therefore improve the better CM energy model performance. And next is some good examples using the AVMAT for modeling. The first example is temperature and cooling demand reduction by green roof types in different climate and urban densities. As we can see, we have the following what-if scenarios. The first is the green roof types. We have the extensive, the bare roof, and the extensive and the intensive green roofs. And for the coverage ratio of green roof coverage, we have 2 scenarios, the full and the semi. For the urban density, we have 3 levels, including the high, medium, and the low. And here we illustrate different urban climates in different cities to achieve the climate condition variation. Introduce some good examples using the AVMAT simulation. And here is the example to investigate the CM benefits of vertical gardening in high-density Hong Kong. And as we can see the what-if scenario, we can consider the green facade ratio from the very low to the 100%. And the greening scenarios, we can attach the vertical greening to all the walls and the different directions of the walls to see the actual impacts. And of course, the surface temperature is our first concern, and next is maybe some air temperatures surrounding the buildings. And the next example is the sensitivity test to investigate the CM performance of different greening scenarios default in AVMAT. And that is to say, we first introduce the 4 greening vertical schemes in AVMAT, and this study is to sensitivity analyze these greening scenarios to see their actual benefits. So let's introduce the different buildings. The domain size is 2-meter grid resolution, and the building size is all 20 plus 20 to 10 height. And the first one is the default building without any greenery, and the building 2 is the building with only greening with low RAI, and the building 3 is similar to building 2 with high RAI, and the building 4 with greening and substrate but no air gap with low RAI, and building 5 is similar as building 4 with high RAI and with substrate but no air gap. And the building 6 and the building 7 is the 4 version with substrate, with greening, with air gap, and the difference is the low and high RAI values. And the meteorological boundary condition is conducted for the typical summer day, and the location is German because AVMAT is it's developed by the scholars from Germany, and using the 4 forcing schemes derived from the EPW files to determine the radiation, air temperature, air humidity values, and the radiation data indicate the clear sky conditions. And here is the general conditions for the simulation day. And here is the results. First, we will care about the facade surface temperature. And for building 1 is the base building without any greenery structures. It displays the rooftop surface temperature exceeding the 55 Celsius degree during the hot afternoon. And the green, then we will look at the green buildings. The green roofs yield much lower rooftop surface temperature of 38 down to 20, depending on the type of greenery. As we can see, the greening buildings all colored with blue. As building 4 and building 5 do not contain air gap, they exhibit the coolest temperature, as roof surface temperature can only be influenced by conduction. And building 2 and building 3 with only green applied have the lowest cooling rate due to the lack of shade provided by the substrate. And building 3, 5, 7 have the higher RAI values, these 3 buildings, for their greenery, so that they demonstrate a strong cooling effect compared to their counterparts. Building 2, 4, and 6 with lower RAI values. So the greenery impacts in AVMAT performs well. Next, we will look at the ambient air temperature reduction. And here is the comparison of air temperature at the potential height between the green and the non-green scenarios at 3 p.m. So the cooling effect is stronger in high RAI greeneries. The lower 3 greens up to 0.8 Celsius degree compared to the low RAI green buildings during the hot afternoon hours. the cool air from building as we all can also see, the cool air from buildings upwind is transferred downwind due to the westerly wind, resulting a minor cooling effect at the outflow boundary in the east. And next is the examples combining AVMAT and Energy Plus. And this study is the energy saving of block scale facade greening for different urban forms. It is a project during my master's program, and we have two parts. The first part is the AVMAT simulation part. We have the following simulation scenarios considering different urban forms, include the different high density, different building density and building rise. And for the greening ratio, we have three scenarios. And we also conduct the field measurement to validate the model is reliable enough to do the further scenario simulation. And after AVMAT simulations, we can get the following outputs, including the air temperature, relative humidity, and the wall surface temperature as the key input to for the Energy Plus EPW files. And for the Energy Plus simulation, we also consider different building prototypes, including the previous code and the current code with different building properties, including the wind-wall ratio, the U value, and the SHGC of glass, and the resolution of thickness, and the internal and external heat gains. And after the Energy Plus simulation, we can go to the data analysis to investigate the energy saving of greening facade buildings and the relationship between energy saving and urban forms, and the separate contribution of shading, cooling, and humidity of green facade. And here is the scenario illustration. We have for the what-if scenario, we considered the urban forms with high and low densities with different rises of high, medium, and low. And for the green facade ratio, we consider the three case levels from none to medium and to high. And for the building typologies, as mentioned before, we use the previous and the current building code to drive the building properties. And here is the model for the vertical greening. We considered all the wall surfaces for the green schemes. And the most important for numerical simulation, we conducted the model validation. We set up different air sensors to measure the air temperature, humidity, surface temperature to between the walls and near the walls. And the model validation shows a good performance for the AVMAT, and it can be reliable for further simulations. And here is the scenario table for including different densities, rises, and the greening scenarios. And here is the results for the AVMAT simulation. We are caring about the effects of green facade on wall surface temperatures. That is the shading effect. As we can see, the west wall had the highest maximum wall surface temperature reduction up to 27 Celsius degree at 2 to 4 p.m. And for the high-rise and high-density scenarios, it has the lowest reduction due to the shading effect of the neighboring closely spaced high-rise buildings. And for the low rise and low density scenario, it has the highest surface temperature reduction because the buildings were low and widely spaced. And the building height is, as a result, building height in the shading effect is more important than building density regarding the shading of green facade. Next, we are checking the effect of green facade on air temperature. That is the cooling effect of a green facade. And this is a picture of diagonal profiles of the reduction in air temperature at the receptor due to facade greening at the block scales in the 6 urban blocks. And the left hand is the low median greening ratio, and the right hand is the higher greening ratio. As we can see, the relative large reduction during the daytime is negligible, and the building density had a larger influence on air temperature cooling intensity than the building height. And here is the picture for the horizontal and the vertical pattern of air reduction at noon in the afternoon for the block scale facade greening. As we can see, the green facade on the building provides a cooling effect separate from the ground to 10 to 20 meters above the roof of the building for the entry blocks. Next, we are checking on the humidification effect by the green facade, that is the effects on the relative humidity. And here is the diagonal profiles of the increase in ambient air relative humidity at the receptor due to the facade greening at the block scale. And the left hand is the median scenarios, and the right hand is the highest scenarios. The results show that the large increase in relative humidity occurred during daytime and negligible at nighttime. And the daily maximum in relative humidity increases ranges from 0.2 to 1.1 percentage for the low scenario, and the 0.2 to 1.7% for the highest scenario. That means building density has larger impacts on relative humidity increases than the building height. Next, we are checking on the effects of green facade on building cooling load. And here is the result for the hourly cooling load and the differences in the cooling load between the bare and the green facade with different building codes and different greening ratios. The results show that the higher greening scenarios had a low cooling load than the median, and the higher scenario accepted greater cooling load reduction than the median, especially for the previous cold buildings. Finally, we are checking on the daily energy saving due to the green facade, and here is the result for the daily energy saving rate and the daily energy saving by the green facade in 6 urban blocks. The results show that the daily energy saving rates of current code were much lower than the previous, and the daily energy saving of green facade is higher, created a cumulative effect and increased daily energy saving unit area of facade greening. Next is the contribution of separate shading and cooling and humidity effects due to the daily energy savings. And here is the result for the relative contribution of shading, cooling, and humidification to the daily energy savings of the green facade. The positive value indicate increasing the energy saving, and the negative value represents decreasing the energy savings. As we can, and the red column is the shading effect, and the yellow column is the cooling effect, and the blue column is the humidification effect. So the columns here tells us that shading provided by green facade is the dominant factors in increasing the building energy demand, as the red columns take the most account. And for the humidification, it had a negative impact on building energy saving. As we can see, the blue bars are relatively small compared to the red and yellow bars. And finally, building energy saving resulting from cooling were mostly offset by the increase in the land cooling demand due to the humidification, and the two components are nearly equal in each case. So that's the examples for the combination of MMAT and Energy Plus to investigate the urban greenery on both the CM performance and the energy performance. Next is a brief model tutorial for MMAT, and if you are interested in, you can visit the MMAT website for more tutorials. MMAT is a commercial tool, so it is charged for the advanced version. However, you can download the free version to test and see what if scenarios, and it is also allowed you the limited grace. And here is the software overview. If you download the MMAT free trial and version, and install the tools, and then you will go to the MMAT headquarters. Here we divided these tools into three main parts. The first part is a preprocessor. It includes the model and the space. They are what we can build a simulation model. And next is the simulation core entry. We have the two tools. The first is to guide you to input boundary climate conditions, such as the meteorological condition, and if you are using the simple or using the forcing or the WRF output data, we can all use in this MMAT guide to drive the meteorological conditions. And then is the MMAT core. It can run. It is after you configured all the settings, it is the run simulation process. And after you conduct the simulation, and we will come to the post-processors. The post-processors include two main points. The first is the biomat to calculate the CM comfort indexes, as we mentioned before, such as the PET, UTCI, and PMV. And the next is the Leonardo. It can visualize the simulation results, including the air temperature, humidity, wind speed, and the solar radiation. And also some heat fluxes we can also visualize by the Leonardo tool. And when we move, this is the first column called MMAT, then we move to the next column called data and settings. For data and settings, we have the following buttons. And the first button is the project workspace organize. It can assign and manage the folder where MMAT were used to store input and output. It is the project manager, and the database manager is where you can edit and create materials, such as the user-defined pavement and the greening and the building envelopes. And then is the Arbor. It is where you can edit and create tree models, especially for the 3D tree models. And then is the Forcing Manager. It is where you can edit your user-defined forcing models for the actual meteorological conditions or the simulated ones. And this toolbar shows the current workspace and folders. And for the database managers, we can edit system materials or create your own user-defined materials here. We can edit the following databases, including the soil profile, the soil, the wall materials, the roof greening, wall, single wall, simple plants, and the pollutant sources. And here is the detailed layers, how we can edit our own user-defined properties. And this is the illustrated for the ground surface and the wall layer. It has different. If you double click, it can show the different layers and the materials, and you can also replace your own materials based on the actual conditions. And next, we would like to introduce the most important tool, the Arbor in AVMAT. It enables us to create our own 3D plants based on actual conditions and the measurement you input. And for the vegetation models, we have the following categories: the simple plants, and you just define the different LAD of different layers, and the 3D trees, you can define the parameters of each layer, including the LAI, LAD, rooftop, and even the tree calendars to tell us what it is, evergreen tree or a deciduous tree. And here is the version 5 enhancement functions to enable us to create the rare trees using the air system plants tools. And next is what we concern about is the facade and the roof greening functions. And here is the detailed steps to set up our own roof and facade greening AVMAT. And after you set up a building, and then you need to convert the version into the detailed design perspectives and shift the view from the 2D to 3D. After shifting, you need to selecting the editing models. Individual segment is recommended here for green facade, and the whole volume is recommended for the roof greening. And choose the material libraries for. Here you can choose the material libraries for wall and roof. For example, this number shows only green for facade, and the second shows the green and sandy loamy with substrate. Next, we are going to introduce you how to create user-defined materials for a facade and the roof greening. First, you need to double-check in the database. You need to double-click the one system greening materials on the left bar, and the detailed layers will show below in the read-only model. So you need to shift in the edit model to enable the greening categories to be replaced by the available plants from the left bar, or you can user define your own plants with the measured inputs. For the user-defined materials, two parameters are key considerations. The first is the LAI, leaf area index. It equals to the total leaf area over the unit area of green roof, one of the most important vegetation parameters. For our model standard LAI for plants are around the following values for different vegetations. For the grass, we set it as 2 to 1 or 2, and for the crops, we set it as 2 to 1 or 3, and the big trees, we set it as 4 to 6. And next key parameter is the leaf angle. For the leaf angle, when it is the illustration for the leaf angle. When it equals to 0, it means the parallel to the surface, and usually we will set this value to 0.5, and it is also default value to represent an average leaf angle distribution at the 45 degree. After the two key parameters, we can then create our user-defined materials for facade and roof greening. Next is the substrate. The substrate consists 3 layers, and as you can see, and each layer can be replaced by a soil profile from the right bar, or you can edit your own user-defined soil profile. Next, for the substrate properties, we have the following parameters, including the immersivity, albedo, water coefficient for plant, and the air gap. MMAT usually considers green roofs as artificially regulated, so this coefficient corresponds to water usually efficiency. And however, not all the researches can be conducted and inputted based on the measurement. So we conducted the sensitivity test to investigate which parameter is more important for the urban greenery in MMAT modeling. And this is what our research team do to investigate the area, leaf angle distribution, immersivity of substrate, albedo of substrate, and the water coefficient and the air gap to investigate which parameter is most important for the model results. After the bunch of conduction, we found that the LAI, the leaf angle distribution, are the 2 significant parameters and should be accurately inputted to ensure the simulation quality. And for the substrate properties, it affects the microclimate, but are less influential than the vegetation properties. And the substrate immersivity greatly impact building wall surface temperature, and it is an accurate value should be used. And for the area and the leaf angle distribution or the substrate immersivity, our team have created a model library based on the vegetations from the South China. So we can, when we model these vegetations, we can pick up the specific vegetation species based on the proposed vegetation libraries. So that's after the urban greenery modeling configurations in MMAT introduction, I would like to give you a brief summary for the workflow of the MMAT modeling. First, we need to set up a workspace and a project folder. That is a priority for the LMAT. If you cannot set up the workspace, the model cannot be created. And then we need to build a model in LMAT using the space toolbar. Then you need to set up initial boundary conditions to drive these simulations, and then you using the AV code to run the simulation. After you got the results, you need to use the Leonardo to visualize the simulation results. Again, here is the workflow for the simulations for different bars and different processors. First, for the first two preprocesses, you need to create model profiles containing the geometry and the geographical information called the INX file. And then, for the simulation engine setup manager, you can use these two engines to create a simulation setting files to tell the engine how to drive the models. And for the next simulation to physical calculation your models, you need to load both the geometry files and the setting files, the files from the two steps to simulate. If everything is correct and pass the model check, then you can run the model and wait for the simulation results. After you got the simulation, we are entering the post-processor to using the biomet to calculate the human CM comfort indexes and load the simulation results and perform extra analysis using the Leonardo visualization tool. And here are some tips summarized for the numerical modeling. First, the model validation and the collaboration is the priority, because this model is developed in Germany, so many configurations and data libraries are from Europe. We need to validate and collaborate based on your own case. Next is the concern for the computational conditions. We need to care about the domain size, the buffer distance, the meshing and nesting grids, as well as the turbulence model to ensure the reliable and accurate simulation. And for the meteorological boundary conditions, if you have no measurement data, you can refer to the Hong Kong observatory weather data for the historical and the current data. And also you can refer to the EPW files to get the typical meteorological data. And for the vegetation properties, the field measurement is necessary to ensure the accurate modeling. If you don't have the field measurement data, and I do suggest you to refer to our tree library based on the vegetation in subtropical South China. After we know what to measure and how to measure, then we need to translate this environmental performance into the credits under the BAM plus Green Building Assessment Framework. And we all know that green roof and green walls can contribute to the credit rating of green building assessment, but the specific categories needed to be clarified. So the Hong Kong Green Building Council have issued a bunch of assessment guidelines, and for today's assessment, we are focusing on the new building version. And here is the category for the BAM plus new buildings version 2.0. including the integrated design and construction management, the sustainable site, and the material and waste, energy use, water use, health and well-being, and the innovation and additions, and the relatively weighting percentage of the first 6 are listed here. As we can see, the energy use takes the highest account. And based on my understanding, I have listed the following categories which green roof and green wall can contribute to the credits for the green building assessment, which includes the SSP1, the minimal landscaping, which is the prioritized, and the SS7, the biodiversity enhancement, SS8, the urban heat island mitigation, and the SS10, the outdoor CM comfort, and the 11, the storm water management. For the energy use, I think the 0.1 low carbon passive design and the 3 peak electricity demand reduction can be relevant. And for the water use, the 0.2 water efficient irrigation and 8 water harvesting and recycling is the most concern for green roof and green wall. And lastly, the health well-being of 0.2, the biophilic design is also considered here. So let's explain one by one. First is the minimal SSP1 is the minimal landscaping, which requires at least 20% of greenery at the site. And I think green roof and green wall area count towards this minimum viable planting coverages. They are counted as the landscaping. Next is the SS7 biodiversity enhancement. It will get the 1 credit and 2 additional bonus and 3 bonus if it is well designed. The biodiversity types green roofs and the green walls can enhance the site ecological value and can support the preservation and the enhancement of the requirements. Next is the SS8, the urban heat island mitigation categories. If we conduct the sustainable building design guideline compliance, we can get 1 credit for the areas less than 1,000 square meter, and for the site above the limitation, we can get the 2 credits and 1 additional bonus. Under these conditions, green roof and green walls are explicit mitigation measures to reduce surface air and air temperatures and are counted towards the SS8 performance. And for the second category is for tree coverage. The trees on the green roofs for the intensive green types can help to contribute to get the 2 bonus, or if it covers more than 20%, it can get additional bonus. And next is the actual urban heat island in studies. Green roof and according to the requirement, I think green roof and green wall can help to reduce the urban heat and the intensity, and the numerical simulation is suggested at the design stage to support the detailed calculation for the heat island intensity mitigation. Next is the outdoor CM comfort part. For it includes the 1 credit for the shaded or the covered routes, and an additional credits can be get if we are passive open spaces with CM comfort. So for the green roof and the green walls, we can consider positive impact by the tree shading and the surrounding ground surfaces temperature of greenery within the site. And for here, the numerical simulation is also suggested. Next category is the category SS11, the stormwater management. For the stormwater management, it can get 2 credits and 1 additional bonus if the green roof and the green wall designed as a softscape to provide the illustration and the sanitation for stormwater, and it can also contribute to the runoff reductions and the peak runoff attenuations. For the energy use, it's indirect calculations for the low carbon passive designs. It can create the 1 credit for the prescriptive path if the vegetated building envelope to achieve the vegetated building envelopes. And I think green roof and walls can also be considered to successfully achieve these credits. And for the energy use of the category 3, the peak electricity demand reductions can also contribute to the passive cooling and the peak demand reduction, supporting the energy-related credits while the reduced cooling load, although it is an indirect way. And for the water use, the 0.2 water efficient irrigation, we can get the 2 credits and 1 additional bonus. Of course, the water efficient irrigation systems for greenery, including the moisture scenario, deep irrigation, and the rainwater harvesting. And for the water use in the 0.8 water harvesting and recycling, it includes the 3 considerations, including the harvested rainwater, the recycled green water, and the exemplary water recycling. We can get the 2 credits and 1 bonus. For the green roof and the green facade, it can be integrated with rainwater to harvest and irrigation reductions to contribute to these categories and meet the criteria for above the 3 requirements. And lastly, for the health well-being for the biphilical design, it provides the 1 bonus and 1 additional bonus. For the green roof and the green wall, it can assembly contribute to biphilical design and improve occupants' connection to nature and meeting the health well-being provisions. So based on the categories above, we need to prepare the required documents to support the credit claims, including the landscape plans, such as the subscape layout showing all greenery areas, planting schemes with species and counties, soil volumes and depths for all plant areas, irrigation provision, and maintenance assessment routes. Our next report documents is the greenery coverage calculation to following the APP 152 methodologies with breakdown of accountable areas, including the primary zoom coverage, the vertical greening within the 15-meter zoom, and the coverage, the greenery above primary zoom, and of course the tree coverage ratio calculation. And next is the tree survey and the assessment report to support the tree survey plans and assessment schedules, highlighting existing and preserve the trees and species, trunk condition rating, and protection measures during the construction. Next is the micro-climatical study reports. For the micro-climatical study reports, the numerical modeling is suggested to provide the detailed calculation with performance criteria. And lastly is the building energy simulations to support the energy-related credits and provide the reduced cooling load based on the energy using simulation tools such as Energy Plus. And that's to conclude, we have 4 takeaway messages. The first is the qualifiable performance of green roof and the green walls. It is not only the decoration features, but also the engineered nature-based solutions to access from the CM energy and hydrological performance to provide the environmental benefits. Next is some key design considerations. As we mentioned in the previous slides, the soil moisture is the critical aspects. If it is not irrigated properly, and the dry soil can cause inversion phenomenon, which will worsen the CM performance of the expected CM and energy performance of green roof and green walls. And the third takeaway message is the multiple method assessment. We should keep in mind that the only field monitoring, numerical modeling, or the laboratory experiment is not enough. We should combine the 3 assessment methods to better and reliable prediction and assessment to support the green building assessment documentation. Next is the BEM plus pathways. We need to transfer the performance-based indicators into the credits to better access the BEM plus green building assessment. Lastly, we should keep in mind that the performance-driven design requires integration, vegetation, substrate, irrigation, and building systems from the very early stage. Thank you for your attention. I will start from the latest question. The latest question is I would like to know if any model software suitable to Hong Kong, South China to simulate a model to evaluate the net carbon impact for preservation of existing mature trees and the different vegetation planting at grade similar to the model of AVMAT. For the CO2 carbon impact, I think AVMAT is the best tool for now for the air pollution and CO2 emission simulations. And the next question is, how would you make to avoid the overrooting and the overgrowing in long term? And I think the maintenance is the first priority. And the next question is for all these measurements, whether there is a common practice during the maintenance period. Besides what professional personnel, whether building surface engine or building surveyor equipped suitable knowledge to conduct assessment together with and consumptions for green buildings. For the measurement assessment, there is actually there is no common practice during the maintenance period, but we can refer to some the guidebook and technical report to get the information to guide the future maintenance period and the measurement. Next is what professional, personal, and whether building service or suitable knowledge to conduct assessment together with energy consumption for the green buildings. And I think for the assessment, first you need to master the energy simulation tool like Energy Plus to provide an accurate and reliable estimation for the energy performance. And the next is, would you recommend local original species as biodiversity is highly promoted by various international institutes? I think for the practical perspective, the native species is more practical and the maintenance in the design, in the projects. But the biodiversity is also recommended to promote the credential gates in under the framework. Yeah, for the I think for the sustainable side 7, the biodiversity enhancement, if we plant the biodiversity species, we can get the additional bonus and get the credits more easily. And for the practice projects, the local native species are always preferred for the better maintenance and the investment. And the first very previous question is this commonly adopted by landscape designers? Do they typically conduct such detailed assessment when designing green wall and roofs? And for the MAT in the landscape design, if you are going to provide the quantitative assessment, they are commonly adopted by landscape design from the research field. And for the design stage, they do not provide such detailed assessment. But if you are going to compare the quantitative assessment and the performance between two scenarios, I think MAT is always the good choice. Thank you for your questions.
Thank you, Dr. Yao, for such an informative presentation. Before you leave, please complete the post-course questionnaire by scanning the QR code or in the link in the Zoom chat to record your final attendance. We would like to extend our special thanks to the Environment and Conservation Fund for their continuous support. Thank you all for joining us today. As part of this project, we will be hosting various courses and events in the future. If you are interested, please follow our official website and social media for the latest updates. If you have no further questions, you're welcome to leave. Thank you.